My name is Vadim Yanitskiy, and today we're gonna talk about, well, I will rather give you an introduction into the recent changes that we implemented for the Osmo radio access network stack. And this topic basically covers two major parts. One is the mult-TRX, another is frequency hopping, and the former is essential for frequency hopping because we implement so-called baseband frequency hopping, and this is kind of based on having multiple transceivers, multiple radio carriers. So just for like some of you who may not be familiar with the hierarchy of the radio access networks in GSM, you always have this base station controller that manages several base station units, base transceiver station units, and one base station transceiver would manage several transceivers, as we usually call them. And well, you usually have 8 time slots in each of the transceiver, and at least one of the transceivers is supposed to be your main transceiver. It's usually referred as C0 or BCCH carrier, and well, it has some limitations and some requirements. What's supposed to be broadcasted on that main transceiver. And one of the limitations or requirements by the specs is the continuous transmission. You cannot have any gaps in the signal. If you don't have anything to transmit, you transmit special dummy bursts that have no meaning, just to keep the full power. And the reason of that is that you want to allow the mobile stations to detect your base station, and well, you don't want this to happen, that like during the full power scanning, the mobile station quickly goes through the spectrum, and at that time you have nothing to transmit, so it will not detect you. That's why you have to transmit like discontinuously. So that's why discontinuous transmission is not permitted on downlink, and BS power reduction or BS power control is also kind of not permitted. You can still enable it, and there are some specification with some constraints and limitations, but generally the rule is that you do not do that. And with discontinuous transmission on downlink, it's also kind of, in Osmo you can enable it, but you will need to cipher dummy bursts, because otherwise, as I think Fireways reported, the mobile stations will have problems with the dedicated channels, and at some point will disconnect and treat the dummy bursts as like channel coding errors. So on the other hand, ciphering predictable bursts with fixed content is not a good not a good idea from security point of view. So that's it. And the first time slot is always BCCH, where you have the special signals, special bursts for frequency synchronization and for time synchronization. And the general rule is that you have one frequency or one absolute radio frequency channel per transceiver. And this is a simplified diagram, and for many people, as I discovered, it's not really clear what's the difference between having multiple base stations on site and having multiple transceivers. So imagine you have some hardware, and the question is should I run, let's say, 3 base stations, or should I run 1 base station with 3 transceivers? And the difference is mostly in coverage. The main idea is that different base stations cover different location areas, and all transceivers of a base station are supposed to cover the same geographical area. So the assumption is that timing advance and all the physical parameters of the link is more or less the same between all transceivers. So that's why you do assignments from the main transceiver to additional transceivers and not hand over, because you assume that the timing advance and the power will be more or less the same. And another restriction is that all transceivers, of course, work in the same band. And frequency hopping that we will be talking later is only possible between transceivers of one BTS. It's not possible to have hopping between different base stations between their transceivers. Another point is scalability, because as I already mentioned, the first time slot of if you have a BTS, you are supposed to have the BCCH carrier, where you are supposed to sacrifice the first time slot 0 as BCCH, where you transmit special broadcast channels and special synchronization channels. And with additional transceivers, you don't have this limitation. You can use all 8 time slots as you wish. And power saving is also one of the aspects of mult-TRX operation. You cannot have power saving on the main BCCH carrier, only on additional transceivers, because again, you don't have to transmit on whole time slots for additional transceivers. This is the only requirement for the BCCH carrier. And BS power control, that's one of the topics that I also submitted for some next OsmoDevCall. You can use it on additional transceivers only to reduce the interference and save some power from the BTS station side. And I already mentioned that discontinuous transmission is only possible for additional transceivers. And if you want to get more official and an overview of the hierarchy according to 3GPP, you may want to have a look into this 3GPP document with symmetrical numbering. And this document is not really about the basics of GSM and introduction. This is about the ABIS interface and about management of different components of the radio access network over the OML link. And if you look at the figure 1, where object model that you kind of see via the ABIS interface, there is site manager, and I'm not sure if everybody can clearly explain what is it for, but the main point is that you may have several base stations on your site, like your physical setup, physical location, and you don't have to use several OML links for each of them. You can reuse a single OML link, and site manager will be responsible for routing the packets between different base stations of your physical setup. I don't think we currently do not support running multiple base stations in a single process in Osmo BTS, unfortunately, and I'm not really sure if Osmo BSC allows you to reuse the same OML connection for multiple base stations, but this should be possible in general. And on the protocol level, you have this specific addressing with transceiver number and so on. And another interesting aspect here is that what we usually call transceiver in generally in Osmocom and in the code, as you will see, the specs define 2 separate entities for that. And one entity is the baseband transceiver, another is the radio carrier. And the key point here is that the baseband transceiver itself is not directly assigned to any particular frequency or a set of frequencies. So it's just like a group of 8 time slots. And channel is exactly how they call time slots here. So it's a channel, or sometimes in Wireshark it's radio channel. And Yeah, it's a time slot in this terminology is basically one physical channel, and it may either be bound to some specific radio carrier or a set of different radio carriers. So, like, just maybe a bit more details on what happens on the OML when you're like connecting the BTS to the BSC. You first have this so-called OML bootstrapping, and one of the OML messages you have is the set BTS attributes, where for the BTS component you basically set the channel number that's where it is supposed to transmit the main carrier, and base station ID code. This is like some other topic that I'm not going to cover here. You also have radio carrier attributes where you define exactly the list of channels. So it's either only one RFCN or several, and several only if your hardware supports this. So this can be used for synthesizer hopping. I will also talk about this later. And for the time slot, for every time slot, you would receive set radio channel attributes message where you have some mandatory information elements like channel combination and training sequence code again, which is a part of base station ID code, if I remember correctly, and two additional optional information elements that make sense only frequency hopping is in use, and I will talk about those parameters later. So that this is how it is happening on the OML link. You don't have there is no special like set attributes message for the baseband transceiver, only for the radio carrier and for channel for GDMA time slot. And in OsmoCom, we have at least for Osmo BTS and Osmo BSC, when they talk to each other, they use OML and RSL over IP. It's ABS over IP. It's non-standard. We basically implemented it in the same way as IP access nano BTS expects this protocol to behave. And what you basically have is the TCP/IP connection, where you have an additional layer of IPA protocol. So I guess IP access, so it's just 3 letters. And it's just more like a header where you have some additional functions and some identification facilities. And I think the most important point of having this IPA protocol is to ensure the packet boundaries in the TCP stream, because you don't have them, you don't know where like specific AML frame, OML or RSL frame ends and where it starts. So this is the purpose. And what happens when you start Osmo BTS? So how exactly it connects to the BSC? It first establishes the TCP/IP connection to the BSC, then the BSC would configure all the managed objects in the BTS, like all the that were mentioned in previous slide here, like channel and BTS and radio carrier and so on and so on. And when everything is more or less configured, the BSC will send IP access specific RSL connect message to every transceiver, every TRX instance. So this means that every TRX has its own separate ABIS connection. And this is what happens. So basically, Osmo BTS receives IP RSL connect from the BSC, and every transceiver then establishes a separate RSL connection. So you have a single OML connection, and as many RSL connections, as many transceivers you have. And the identification of a particular transceiver is done using the already mentioned the IPA protocol, where you have unit ID. It's basically a combination of three numbers: site ID, BTS ID, and transceiver ID. And also in this IPA header, you have 1 byte that allows to distinguish between different transceivers in the BSC. And if you want to have a multi-TRX setup, a reasonable question is what kind of hardware to use for that. And if you look at commercial BTS hardware, you may see that Nano BTS kind of supports the multi-TRX, because several devices can be chained together using the proprietary timing interface bus, as far as I remember. And we even have a wiki page about that. And the only problem is that this interface requires you to use a very specific and I would say rather exotic RJ69 cable. And I'm not sure if it's really easy to buy already made cables. So you probably have to do it yourself. And there is a limitation of how many Nano BTS units you can connect together, up to 4. So you can have up to 4 transceivers. So basically BCCH carrier and 3 additional transceivers. With Osmo BTS, I'm not really sure. As far as I know, some models have 2 transceivers on board, and this means that you can get up to 2 transceivers. I'm not sure if the second part of the radio can be actually used as a transceiver. Maybe it's only as a separate base station. So probably it's only multi-BTS. I'm not really sure. And this Siemens BS11, there are different configurations of this hardware. So either a single TRX or 2 TRX, or I think multi-TRX configurations also exist. And with SDR-based hardware, it's a bit easier because, basically any full duplex SDR that is supported by OsmoTRX, like UZRP or the Lime SDR, you can use it. And there are 2 modes of operation for multi-TRX. One is when you on some models, some SDRs, you have 2 channels. Like on B210, you have 2 channels. So you can run 2 transceivers on those channels, and with multi-AFCN mode, you may run up to 3 transceivers on a single physical channel, and all the multiplexing and demultiplexing is done in software. So this results in in relatively higher CPU load, and there are some restrictions, like you have to follow some specific fixed spacing between the channels. If I'm correct, 4 channels between your transceivers. And there was some related discussion why this requirement is the case. And there was Thomas responded, at least explained why and so on. And there was also an important backfix that we had problems with the antenna configuration. So in multi-RFCN mode, only 2 transceivers would work. And if you configure 3 transceivers, the OsmoTRX would crash. So we fixed that. So now you can run 3 transceivers. And in case if you want to give it a try with the first mode of operation, where you have 2 channels, 2 independent channels, physical, you basically disable the multi-IFCN mode and just configure 2 channels in the configuration, and that's it. So OsmoTRX will start with 2 channels that you can use as you wish from the higher levels. And in case if you have some SDR that has only one channel, you can enable the mult-TRX mode and configure up to three transceivers, up to 3 channels here. So yeah, and in Osmo BTS there was a lot of code refactored by Julie long time ago, and there was this really nice abstraction concept of the PHY and instance, and thanks to some fixes by Pao, we can now specify the number of transceivers dynamically in the config file. Before that, you had to specify the number of transceivers using the command line argument, which is quite ugly. And there was another annoying bug in Osmo BTS related to the FN advance, where the FN advance would increase for each transceiver being handled. Then this, so far nobody noticed this, probably because not many of us really running mult-TRX setups. So this is a configuration example. If you want to configure, like, you basically specify one PHY. So this corresponds to OsmoTRX process, and instance here means channel basically. And in the BTS section, where you specify transceivers, you refer to particular PHY and particular instance of that PHY. So that's it. That's all you need for the mult-TRX and the BTS. And in the BSC, it's a lot easier, because Osmo BSC was designed with mult-TRX support initially, I think, and for IP access BTS models, as I already mentioned, you have separate links, and you basically introduce additional TRX nodes to your configuration file, and you're done. So regarding the limitations, OML, in the OML header, you can have up to FF in hex instances, P or BTS, but some of the numbers are right. Yeah, in OML it is the case. I think it's 249 or so, because the FF is reserved for with a special meaning for like everything. All and in the IP access specific header, you have probably as much identifiers as here, but some of them are also reserved for OML and some for Osmocom specific extensions. And on the PCU interface, the interface between BTS and PCU, you still have this limitation of up to 8 transceivers per BTS, and as I already mentioned, one Osmo BTS process allows you to run only one BTS instance. And we received some nice news that some customers had rather positive experience operating mult-TRX setup with 8 transceivers. And in our test setup, where we simulate the interface and run TTCM3 tests against the BTS, we have 4 virtual transceivers, but unfortunately no mult-TRX test cases so far. And this brings us to the next topic, frequency hopping. And I borrowed the pictures from the talk by Piotr from OsmoDevCon 2019. And just a brief introduction. So what is it about? Frequency hopping in GSM is, and everywhere basically, is a sequential change of the transmit and receive frequency. And then in GSM in particular, it's slow hopping if you compare it to Bluetooth or other technologies. So in GSM, basically more than one symbol is transmitted per frequency. It's the whole burst that you transmit, and for the MS side, it happens once per TDMA frame, so yeah, close to 5 milliseconds. And frequency hopping is only possible for dedicated channels. BCCA shall not be hopping, and well, the purpose of frequency hopping is to reduce the call channel interference. So you basically spread your transmission across the spectrum, and even if you have some like interference source on some particular frequencies, not all, at least not all of your information is affected by this source of interference. And there is a myth that it improves security of dedicated connections, or like this one is not the myth itself, but it definitely doesn't make the interception impossible, just makes it harder. And yeah, nothing special about that in terms of security. And the algorithm itself, the algorithm of changing of sequential frequency changes itself is defined by 3GPP, and there is two kinds of hopping. One is just sequential, so if you have, let's say, 3 channels, it will just hop between those in sequential order. And there is pseudo-random, that's kind of sophisticated algorithm by 3GPP, where like it's not secret at all, everything is specified, and you basically have 3 parameters that define the hopping sequence. One of the is the mobile location. It's basically a set of channels where you like transmitting, and the hopping sequence number. This defines the type of hopping sequence generation, either sequential, if it's 0, it's sequential, and the other one is the pseudo-random. And for the mobile location index offset, you basically can shift the algorithm in like, so it doesn't clash with the other time slots or other hopping time slots. And for the given TDMA frame number, the formula is basically very simple. You have some function that I'm not going to list here to discuss the details and so on. And just, yeah, you provide all those parameters and the current frame number as the input, and you get the channel number to where to receive and where to transmit as the output. And when it comes to implementation of frequency hopping, there are two main approaches. One of them is baseband hopping, where several RF carriers just stay on fixed frequencies and do not change the frequency. So basically, you have multiple transceivers and multiple receivers, and in the terminology of 3GPP, they are radio carriers. And for TDMA scheduler, you need, in the scheduler itself, you just need to route bursts between those radio carriers. And this approach is relatively easier to implement compared to synthesizer hopping, and this is exactly what we support in Osmo BTS and Osmo TRX so far. I think for Osmo BSC there is no difference. It's on the higher levels of the stack. And for synthesizer hopping, yeah, it's basically when the RF changes frequency for every transmitted and received burst. To requires more sophisticated implementation, the hardware itself must be capable of retuning the frequency quickly enough. And yeah, there is a talk by Piotr Krysiek, the author of GSM, about implementing the hopping for the mobile station side. And this is where you cannot have baseband hopping because, well, you don't want to set up I don't know how many transceivers use SDRs for like to be able to talk to commercial networks. So synthesizer hopping is the only way for the mobile station. And if you want to get more details, you can watch his talk. I think the slides will be available, and you can click on that link later. And this is also some graphical representation of how the transmission happens. Transmission of a single frame that consists of 4 bursts. So basically, this is what's called sequential hopping. You have 4 transceivers, and burst ID 0 goes to the first transceiver, and burst ID 3 goes to the last transceiver. So where the scheduler then kind of reorders all the bursts and decodes them back into the CCCH, like SDCH or whatever frame, and then BTS basically forwards it to the BSC. And well, what do you need to do if you want to have frequency hopping? You first need to get to make sure that your radio supports it. And if I remember correctly, this BS11 can do synthesizer hopping, and for baseband hopping, you need like several 2 or more radio carriers, and the PHY itself, the BTS, must support hopping. And unfortunately, as far as I know, NanoBTS, neither NanoBTS nor SysmoBTS does support hopping, because they like the way that OsmoBTS operates and talks to them is on the higher levels compared to the SDR approach. So you basically send layer 2 frames to the DSP, and you get layer 2 frames from the DSP. So there is no way to control what frequency is used for like the actual burst transmission. And for the SDR-based hardware, it's easier because only user-IP can do mult-TRX. Unfortunately, for line SDR, it should be also possible, but nobody implemented this on OsmoTRX so far. So if you want to play with frequency hopping, either get BS11 or some user-IP. And this is a configuration snippet that you can use in the BSC. So basically, you go to the TRX section where you have all your time slots, and in this example, the hopping is configured for a single time slot 7, and you go to this section and enable the hopping itself, and configure the sequence number and the offset for the hopping sequence generation. And you have to explicitly list all the carriers, all the channel numbers that are involved in the hopping. And you do the same for all time slots that are involved. Let me try to show you the difference. So the difference here is that, like, this one is the time slot 7 on transceiver 0, and this is the time slot 7 on transceiver 1. And the only difference here is the mobile location index offset that must be different for all time slots in the mobile location, while the hopping sequence number must be the same. So this way you don't have situations where bursts get transmitted by different subscribers at the same time, or like received at the same time. And that's mostly it. So you don't really need to do anything else apart of this a bit complicated configuration in the BSC. And here is a little demo that I recorded some time ago. So yeah, just a typical network in the box setup where I currently have no subscribers connected, and this famous GR phosphor by Sylvain. And what's happening here is that on the left, from the middle of the spectrum, you have the main BCCH carrier of my setup, And on the right, symmetrically, you have another transceiver, another carrier that is currently not transmitting any signal because, well, it doesn't have to transmit anything. There is no subscribers, no channels allocated on it. And at the time I'm switching on the phone close to my setup, and here you see some bursts appearing on the spectrum, like some of them. Some of the bursts will go to the BCCH carrier. Some of the bursts go to the additional transceivers. We have a subscriber attached. And for the better demonstration, I'm establishing a silent call with the type of it's basically TCH in signaling mode, and yeah, that's nothing special, but it looks a lot better on the uplink part. So this is how it looks like, and if you stop it for a second, you see that bursts are bursts come the spectrum with the offset. So this is exactly what we expect to see here. Yeah, this is how it works. So some bursts go to one carrier, some bursts go to another. And if you establish a TCH in speech mode, it will be even like more visually easier to see what's happening. Yeah, it's quite an old video from the beginning of this year. Yeah, this is the TCH on a hopping between two carriers, and that's mostly it. Yeah. What regarding the problems and limitations of our current implementation, one thing I noticed while setting up the test setup for our TTCM3 stuff is that the BSC, the VTY interface in the BSC is not really convenient for configuration of the hopping parameters, because it was designed for more like for synthesizer hopping, where the approach itself is low level because you just specify the channel numbers and it works. And with baseband hopping, you may easily end up in a situation where your configuration is either completely wrong, or at least it works, it starts, but some bursts are getting lost, and it takes some time to investigate what's the problem. Yeah, and one of the reasons of that is that you specify the hopping parameters in time slot section of the BSC configuration file, and given that you have 8 time slots, it's time slot 1 of transceiver 0 and time slot 1 of transceiver 1. They can be quite far from each other. There's a few screens, so it's not, you don't see all the picture in one screen, and it's easy to either add some non-existing channel to the mobile allocation, or to specify the same index offset and so on. So one of the ideas that I have is to introduce a separate node for the frequency hopping parameters, where you could specify a kind of groups of different parameters, but this can be discussed later. And regarding performance, in Osmo BTS, we have, at least for the downlink, we have a cache. So basically an array of pointers where the index is the channel number and the value is the pointer to the transceiver. So everything is easy, and on the uplink it's unfortunately not that beautiful, because I tried to create some representation, very simplified, of the algorithm of what happens when we receive an uplink burst on a time slot where the hopping is enabled, and what happens is we basically brute force all possible all time slots of the same number on all transceivers, and see if the channel number for this specific frame number matches. So I'm currently thinking of a way to optimize this somehow, because I think it negatively affects performance if we do this for each burst. And there are some non-obvious problems that we recently experienced in real setups. Is first of all your messages on DCCH, like assignment messages, and especially the handover command and the assignment command, they are getting longer because you need to include the hopping parameters. And this involves the LAPDM fragmentation if the message is longer than 23, or I think it's even less octets. So imagine a situation if you have a handover because of caused by bad receive quality or bad receive level, and one of the LAPDM segments get lost. So it's most likely will be an unsuccessful handover or an unsuccessful assignment. So the solution for that is proposed by 3GPP itself. It's different encoding algorithms for the mobile allocation. It's basically a bit mask. In the simplest case, it's a bit mask, and they propose some codings that reduce the size of the information elements. And this is currently not implemented in Osmocom and needs to be investigated. And yeah, in this amazing book that Harald recommended, this evolution and performance of GSM and Edge, they also discuss this problem and some real simulation results. So we should check out this book if we want to find a solution for that problem. And that's it. Thank you for your attention, and I'm happy to hear your questions if you have any.